In this video, we're going to talk about what are known as slant asymptotes. In our exploration of the graphs of rational functions, we have talked so far about horizontal asymptotes, we have talked about vertical asymptotes, and we have talked about holes in the graph. So a slant asymptote will arise when there is not a horizontal asymptote. And it'll happen in a very specific way. So, for example, if we were looking at this graph and we, as we do with horizontal asymptotes, we say what happens as x gets really, really big in the positive direction. We know that we would look at the highest powers of x and their coefficients. And so in this case, this would act very much like x squared over x, which is really just acting like x. Now, as x grows large, this is going to go to infinity, so we would say there is no horizontal asymptote. And that is true, but because the degree of the numerator is 1 larger than the degree of the denominator, so I'm going to say that degree of numerator is 1 plus the degree of the denominator. When that happens, we will, and only when that happens, will we get a slant asymptote. So what the idea behind it, let me see if I can spell asymptote correctly. So, which we will abbreviate as an SA for slant asymptote. So the idea is, as x gets really, really big, even though this is not going to approach a finite number, which is what we need for there to be a horizontal asymptote, it is going to act like some kind of line. Now, you may think it's going to be just y equals x, but we don't really know that yet. We're going to have to do a little bit more analysis. But at any rate, because the degree of the numerator is 1 bigger than the degree of the denominator, the ends of our graph are going to look like some kind of straight line, and we're going to have to figure out what that is. Now, it is true, although we aren't going to worry about that, if the degree of the numerator was 2 bigger than the degree of the denominator in something like this, it would, at the very ends of the graph, approach some kind of parabola. And you could go on and on with this analysis. But we're not going to worry about this. And the truth is, when you get that far out there, the interesting stuff's going to happen somewhere in the middle. And by the time we get to the end behaviors, they're just going to look like they're very steep. It's not going to be, most of the time, very recognizable as a parabola or a specific parabola. But we're not going to worry about that. We are going to worry about slant asymptotes. So what we're going to do is we will still see that, as we have seen before, because the denominator is x plus 1, we're going to get a vertical asymptote of x equals -1. We can try to factor our numerator in a search for a hole, but because the x minus 1 does not cancel with the x plus 1, there aren't going to be any holes in this graph. So what we know so far is that, our graph is going to have a vertical asymptote at x equals -1. So I'm going to put that in there for now, and then let's talk about the whole slant asymptote thing. What I'm going to do now is I'm going to take our original and I'm going to divide the x plus 1 into the x squared minus x. Now I can do this either long division like I have set up here, or I could do it synthetic division. It doesn't really matter. I'm going to work a second example in a minute, so I'll do that one using synthetic division just so you can see it. But since I have this already set up, I'm going to go ahead and do long division. So I'm going to say x times x is x squared, x times 1 is an x. When we subtract those, the x squareds drop out. A negative x minus x is going to be a negative 2x. So I come back up to the top and I say, I need that to be a -2. So a -2 times x will give us a negative 2x, and we'll make that a minus 2. When we subtract the negative 2x's, we'll cancel, and 0 minus negative 2 will be 2. And so we are going to get our remainder over what we divided by as a fraction. So let me make this clear. I want to emphasize the equality of this. So this rational function that we started with is equal to x minus 2 plus 2 over x plus 1. So they're just two different ways of writing the same thing. But now, if I think about what we were doing before, when we were looking for a horizontal asymptote, if I look at this expression and I take the limit as x goes to infinity, then what happens to this remainder fraction as x gets really, really big is that is going to go to 0, and our graph is going to look more and more like y equals x minus 2. This is going to be our slant asymptote. So I'm going to take this to our graph where we've already put in the vertical asymptote. And now what I'm going to do is plot this line y equals x minus 2. So it's got a y-intercept of negative 2, a slope of 1, and I'm going to graph that, and I am going to label it. So that's going to be y equals x minus 2. Now, in a sense, what we're getting here is kind of like we've seen graphs before, where we had a vertical asymptote and a horizontal asymptote, and it kind of acted like a new set of xy axes. And so you sort of have a quadrant 1, quadrant 2, quadrant 3, quadrant 4. That's still true in this case, except our horizontal asymptote has been tilted sideways. But there's still a sort of quadrant 1, quadrant 2, quadrant 3, quadrant 4. At any rate, the slant asymptote is just a guide. The vertical asymptote cannot be crossed. So as we saw in the case with a horizontal asymptote, I'm going to plot a point on either side of the vertical asymptote. So I'm going to go right of x equals negative 1, and I'm going to plug in x equals 0. Now, because of the equality of these two expressions, I can plug the 0 into either one of these, whichever I think is easier. In this case, I kind of like that first one there. If I plug in 0, we're going to get 0 on top, and so that's going to give me 0 pretty pain-free. So I know that 0, 0 is going to be a point on our curve. Now, as x gets really, really big, as we saw down here, it's going to, in the positive direction, it's going to approach our slant asymptote. Now, as I approach that vertical asymptote, we have to do our analysis again. So I'm going to say x is going to approach negative 1 from the right. Now, here's where it gets kind of interesting. What's going to happen as we approach negative 1 is this remainder part is going to get huge, because as x gets close to negative 1, the denominator of this expression is going to get very, very small. And so a number that's not 0 divided by a very, very small number is going to go to infinity, either positive or negative infinity. Now, what's happening over here really doesn't make much difference because it's just going to be a finite number anyway. So what we look at as we take the limit as x goes to infinity is just the fraction. And the 2 is always positive. As we approach negative 1 from the right, like plugging in something like a negative 0.9, the x plus 1 on the bottom, the negative 0.9 plus 1, will be a very small positive number. And so, because you have positive divided by positive, it's going to go to positive infinity. And we know our graph is going to take off and go up. Now let's do the same kind of thing on the other side. This time I'm going to plug in -2, and again, you can choose either form of it. I kind of like this one over here. So if we plug in -2, we're going to get -2 squared is 4, minus a -2 is going to give us 6, and -2 plus 1 is -1, and 6 divided by -1 is going to be a -6. So back to our graph, if I can get my pen to cooperate, and it's not right now, then I've got 1, 2, 3, 4, 5, 6. So I'm going to be down here, and I've got -2, -6 is going to be right in here. And so we know that as x goes to -infinity, our curve is going to approach that slant asymptote. And if I take the limit as x approaches -1 from the left, again, I'm only looking at our fraction, that 2 over x plus 1. So if I plug in something just to the left of -1, like say -1.1, the positive 2 is always positive, but the -1.1 plus 1 is going to be a small negative, and so that is going to go to -infinity, and our curve is going to dive down. So there we see the graph of a rational function with a slant asymptote. Let's try another example. So in this case, we're going to say y is equal to x squared minus x minus 2 all over x minus 1. So if we are looking for our horizontal asymptote, we take the limit as x goes to infinity. We look at the highest powers of x in the numerator and denominator, and we see that that's going to go to infinity, so there is no horizontal asymptote. But in the course of doing this, we see that the degree of the numerator is 1 larger than the degree of the denominator, so that means we are going to get a slant asymptote. Now, the last example I did long division. This time I'm going to do synthetic division. Since we're dividing by x minus 1, I can do synthetic division by putting 1 in the corner box and writing the coefficients across the top. And I'll get 1 times 1 is 1. There's a 0. Going to get another 0 here. Adding down is going to be -2. So what we're getting here is that our x squared minus x minus 2 over x minus 1, that rational function, is equal to x plus the -2 over what we divided by x minus 1. These are equivalent to each other. So I can tell that this, as x goes to infinity, so in my head, you don't have to actually write this, but as x gets really, really large, this fraction is going to go to 0, and our polynomial is going to approach y equals x. So we are going to get a slant asymptote of y equals x. As before, we can tell that this is going to have a vertical asymptote at x equals 1, where the denominator will be 0 and our function will be undefined. So let's see if we can put it together in a graph. We've got x equals 1 is going to be our vertical asymptote. So I'm going to put a dotted vertical line in there. Call that x equals 1. Our slant asymptote is y equals x. So that's going to have a y-intercept of 0, a slope of 1. So it's going to look like a 45-degree angle line going through the origin. And I'm going to call that y equals x. I'm going to plot a point on either side of the vertical asymptote. So I'm going to plug in 2. And if I plug in 2 for x, let's see, I don't know if it much matters. I think I'm going to choose this version right here. That to me looks easier. You may disagree, that's fine. I'm going to go 2 plus negative 2 over 2 minus 1 is 1, and so that is going to be 0. So 2, 0 is going to be a point on our graph. We know as x goes to infinity, it's going to approach that slant asymptote. And I've got to do the analysis. What happens as x approaches our vertical asymptote from the right? As we talked about before, I only have to worry, in the case of the vertical asymptote, of that fraction, the remainder fraction. It's always going to be a negative 2 in the numerator. As we approach 1 from the right, like plugging in a 1.1, we're going to get a small positive number in the denominator, which is going to make this go to negative infinity. As it kind of looks like it wants to do anyway, it's going to dive down. I'm going to plot another point, so I'm going to plug in 0. And this time I kind of like the first version there, because all those x's are going to disappear, and we're going to get a negative 2 over negative 1, which is going to be a positive 2. So that's going to make the point 0, positive 2 be on our curve. We know as we approach negative infinity, as we go way out there to the left, our asymptote is going to get closer and closer to that slant asymptote. I'm going to do the analysis. What happens as x approaches our asymptote, 1, from the left? I'm again going to look just at that fraction remainder. The numerator is always a negative 2. If we plug in something just to the left of 1, like say 0.9, then 0.9 minus 1 in the denominator is going to be negative, and so that is going to go to positive infinity. It's going to take off and go up. All right, very good. That's the idea behind slant asymptotes.